we are having a new beginning, and we will go through this in a much more slower fashion because these were not published earlier than in the book. So I will try to explain some constructions and concepts required to solve the membership problem for the pedigree polytopes. Here I am actually explaining the different steps I have taken to devise a new way of approaching this membership problem for pedigree polytope. First thing is, given an x, it is in R or Q plus tau n. That's the order. It's of the order of n power 3. That means if you have 10 cities, you will have 1,000 coordinates like that, of the order of 1,000. Now, instead of working in that dimension, usually for the other combinatorial problem, we work with the dimension in which the x is and then try to say whether it is there in the polytope or it is, if it is not there, give a separation hyperplane, etc. Now, I get a clue from how they study protein. If you look at protein, there are also actually long chains of codes. Of course, they are not only 0 and 1 codes, but they can be written as 0 and 1 code, because for each amino acid you can give a particular 0, 1 code, and so the whole thing will become a chain of amino acids, etc. Now, but they don't study it in that large dimension, but instead they study how a protein folds itself in a 3-dimensional this one, and then they classify them as different proteins, so identify them based on the shape, etc. So it's a good idea not working in a higher dimension, but to work in a dimension that is easier for us to look at or do something in a lower dimension. So here what I do is, instead of working with the tau n dimension thing, I'm going to take these xk's, x4, x5, etc., each one as a vector, and then taking the adjacent ones, we can define a fat problem, okay, a flow feasibility problem. And once we know the conclusion about this, we will add the next level like that. So if it is failing in this level, we don't go further. So you can see the scheme, which is, of course, I'll be from k equal to 4, 5 like that, but anytime it fails for a particular k, we don't have to go any further because that's the result we got earlier. So we can use that we don't need to do anything further. But if we proceed further, what needs to be done? That is the next thing. So here again, I'm defining, not working with the actual, the higher dimensional thing, but we are going to work with a layered network. What is meant by a layered network is you have a first layer, a bipartite network, then you add one more layer, so that becomes with a 2 bipartite network. The thing is, no arc is there from the first layer to the third layer. So it is all only between first and second and third like that. The arcs are not elsewhere. That's how it is called a layered network. So you can imagine, like, you have some cities to go to some other cities, but only between these two cities you have roads. After that you have another set of cities. They can only be reached from the next second set of cities, not from the first set. So that way you will get a layered network of cities and things like that. So similarly we do it here. So we first define a layered network for k equal to 4, which covers up to the 5-city thing, 4 and 5 cities. And depending on the result on that, we go whether to build further or not, or stop. So we are able to prove necessary result when we should be able to proceed further, when we cannot, etc. And these things can be done easily, is what we have to prove afterwards when we check the complexity of this approach. First, I will explain how this layered network is made. This requires keen attention. So if you don't get anything, you can ask me questions. We can stop and review that. We'll also take examples to understand what's happening, so that the construction of the network or the layered network is very clear. So for instance, how I am taking the higher dimensional vector of zeros and one to a lower dimension or a two-dimensional lattice with some weights on these lattice points. That's how we are converting that. That is, the given weights, x, having different values, because we are talking about not a pedigree, so there will be fractional values also for the x. So, but it is of the length tau n. That's what is important for a given n. So here I am taking, say, 6 city, this one, so n equal to 6. So if you look at the x given there, which is, I can just, of course, I can read it out, but it will be boring. 0, 1, 0, 0.5, 0, 0, 0.4, 0, 0, 0.1, 0, 0, 0, 0, 0, 0, 0.5, 0.4, 0, 0, 0.1. So, of course, that's the vector given. And that corresponds to n equal to 6. Okay. Now, we already have checked, because this must be in the PMI-N. That means it should be a solution for the PMI relaxation problem. That can be easily checked. And for instance, we have for 4, it is 0, 1, 0. That means we are inserting in 1, 3. Suppose you have ordered the pairs 1, 2, 1, 3, 2, 3. Then this means 0, 1, 0 means we are inserting between 1 and 3, 4. And that is for certain. That's why we are having 1. Okay? And then for 5 we are saying we insert with half of that between 1 and 2 and nothing in 1 and 3. And 2 and 3 we insert 0.4 of that. And 1 and 4 nothing, 2 and 4 nothing, and 3 and 4 we insert 0.1 of that. That means we are actually inserting 5 in a fractional manner, not in one particular this one. Okay. Now, is this solution satisfying the MI? This one can be easily verified. What we need is, for everywhere I am able to insert, that edge must be available. Actually, if you look at the tour, corresponding tour, we can see that all these edges 1, 2, 2, 3 and 3, 4 are available in that. So we are only inserting in those places, but with some fractional value. So all these are feasible. Okay. So that's a very easy to write that. And similarly, you can write for 5 the corresponding edges with the weight. And then in C6 you can check whether these weights are less than or equal to what is already there. That's all you have to do. So you can check first. The exercise would be to check that this solution is MI feasible for 6. Lattice on the weights on a two-dimensional lattice. So what we do is, on the x-axis you can consider you are having 4, 5, k, etc. n. On the y-axis you can imagine you have 1, 2, 1, 3, 2, 3. That means all the pairs are arranged in a particular order and going up to n minus 2, n minus 1, because n can be inserted in one of these things, so it is up to that you can go. And take any one of those places. Now you can see that for 1 to 4, there is a coordinate. If that coordinate has a positive weight, you put that as the weight there. So that will be your third dimension. You can show it in the z-axis, how much is that. So for each k you can do this way, and that will add up to 1, etc. So you now have a picture as shown in that figure 5.1, or I have reproduced here. Is that clear what we are doing? We are taking a higher dimensional vector of belonging to R tau n, and then we are trying to look at it as a two-dimensional lattice with the weights there, etc. Now, this is only for visualization. What we are going to do is to take layer by layer. That is, first we take 4 and 5. So we get a fat problem. That is, we have some availabilities, some requirements. Can this be met with only the non-forbidden arcs? If that is feasible, that problem is okay. We can move on to the next one. But we will do something more here. That is, if it is feasible, we try to find out an interesting thing. The flow along any of the arc, is it same in every feasible solution? Such a flow we call it frozen flow because it is not changing. And such an arc is called a rigid arc. Okay? And the rigid arc will have frozen flow which is positive. Supposing your frozen flow is 0, that means in that arc no flow can be there. That means that's a dummy arc. That means you don't have to have that because you know there cannot be any flow in that. So if we can find in every solution the flow is same along that arc, then we will be able to define, able to identify that is a rigid arc. And if the rigid flow is positive, that's a frozen flow. If the rigid flow is 0, then that arc can be removed because there cannot be any flow, and then have a feasible solution. So that's a nice idea. And how do you find that? How do you find the rigid one? That is an interesting question. So you may, now it might look everything, you don't know why I'm doing that. But it will be clear later. At this stage, I'm saying that I'm going to define these things because there is a need for that. You just can accept it. Right now, to motivate, I need the whole thing. So I cannot do that right now. But I can just explain that I need to find these things, and that will be useful in the construction. Okay. So you can imagine that if you have built the network up to some k minus 1 or up to k, then I'm going to tell how you can extend it to the next level. Because we don't have to extend immediately to n, because we know unless it is going to be okay, for the next we don't have to go till n because we may stop also, okay? So a current network for xk we have. How to build that we'll talk about, or assume that it is there. For instance, for 4, if I have done, I have a current network. Okay, that will be easy to do, I will do that. After that, how to construct is that we have the origins for the next bipartite problem, but this origin might include some more nodes corresponding to rigid pedigrees, which those are all having rigid means because that flow along that has to be always the same. So those rigid pedigrees will become also as origins. Then we have, of course, as in the earlier case, you can have the destination is corresponding to the xk plus 1. It is. So for all the edges in k plus 1, ek plus ek, you will have some weights. That is the demand in those places. Now, if we can solve this problem, the fk, we define, of course, here still I have not told which of the arcs are there between two. This one. This is where so if you have got this one, that is, I'm going to define a fat problem based on the current network, the last stage, and the new stage added, that is the xk values corresponding to the new stage. Now, we have the origins, we have the destination. We need to know the arcs or the edges. So how I define is, it's very simple. Again, intuitively, what I try to do is, if I have an arc any positive flow in that I must be able to get through pedigree. That means we must have pedigrees that can bring that flow there. Okay, so these pedigrees will be available as paths in this network or in the rigid pedigree. So if it is a rigid pedigree, there is no problem, because we have to only check whether that edge is available, a generator for that is available. If that is there, we can connect it. That is similar to what we have done earlier. But for other ones, we have to ensure that we do have some pedigrees that can bring that flow along those paths. And if that is not possible, that means the maximum flow that can come is 0, then that arc cannot be there, because I cannot have some a way I can get a new pedigree made for the next stage. So this is the basic idea. So what I do is, I will first explain how we construct the network for k equal to 4. That means involving the 4 and 5, there's vector x4 and x5, and the solution of that, and the rigid arc, how we find, etc. Actually, finding the rigid arcs among the bipartite flow problem has been studied by other people for different reasons. For instance, if you are having some table government has created some table based on census data, which is a two-way table. That is, you have one rows and columns, and there are numbers in that. And people have got the right to know certain things, so they are giving that information. But at the same time, government has to safeguard your private information. Now, by giving some of these things, if they can get the private information, that's not a good idea. So how to prevent this was one of the problems. And that as a similar question. That means it is a bipartite flow problem, in that the flow along some of the things you cannot give. If you give, they can find out all the flows. So which are those arcs which you should not reveal? That's the kind of problem they solve. So there is an algorithm done for that, and that is given by Gusfield. So we will call that frozen flow finding algorithm. Of course, you can implement it using different subroutines, but the basic idea is given. I will explain this frozen flow finding algorithm separately in another video. We can use that, of course, algorithm here to find the rigid flows and dummy arcs, etc. So I briefly explained how we will go about constructing the layered network for K. Of course, there are many things that you would having questions about why do we construct this, etc. We'll come to that later. First, get the construction clearly. So now I will, because I said we have an existing network, so where do we start? We start with the first two layers, that is corresponding to k equal to 4 we are going to do. So corresponding to 4, you have the x4 vector and x5 vector. So use the edges in E3 as the origins and give the weights according to x4 along this one. That is the availability. And for x5, then you have the edges in E4. That means 1, 2, 1, 3, 2, 3, 1, 4, 2, 4, 3, 4. These are the edges. And we have the corresponding x values. So that x5 values, so they become the demands. Of course, now use which are the arcs that are forbidden, because for each of these edges in the 4, k equal to 4, that means the x4e, those edges, each one correspond to a Hamiltonian cycle. So if any of these edges are available, for the edges that you are looking for, x5 e prime, let's say, is positive. That means you want to have some positive demand there. That means that e prime must be available in one of these edges. So that's what we call, or you can put it another way, that E prime has a generator in this pedigree corresponding to that. Both are okay. Now you connect such arcs. So you are getting a bipartite flow network. Now you want to see whether this is feasible or not. That's it. Okay. Now if this is feasible, then we know that x given 5 is in convex P5. If it is not belonging to that, we can stop, because we know that x given n or x given any other k cannot be in the convex polytope, corresponding convex polytope, convex combination of pedigrees there. So those flows which will remain frozen or same for all feasible solutions. You have one feasible solution. For any feasible solution, if the arc flow is going to be same, then that becomes a rigid or frozen flow, and there's a rigid arc. So you have some examples to consider. Okay. So it's easy to see whether we have a feasible solution. And once you have a feasible solution, using that feasible solution, we can go to the frozen flow finding algorithm, and it will identify which of the arcs are rigid. And those rigid arcs with positive flow will become, of course, give you the rigid arc with the corresponding frozen flow. And those rigid arcs with zero flow will be dropped from further consideration, because they are dummy ones, because no flow can be there and you can still be feasible. Okay. Of course, still one more step is there. That is, once you have identified the frozen flows for any of the arcs, remove that frozen flow from, of course, you can update the capacity of this one. Of course, if you assume the capacity is equivalent to the origin availability, you can remove the flow along that. And also, because if that arc is rigid, means what? The flow has to be same in all. Okay. So once we are removing, there won't be any more flow we need to consider, so we can forget about that arc. Okay. But then put that arc as one of the rigid pedigrees. Here it is a pedigree for 5. So put that as one in the set of pedigrees. We call that set R4. R4 has rigid pedigrees with the corresponding value, and that is mu corresponding to that. So you have the weight as well as the corresponding pedigrees. So that is what is our final N4, this one. That means N4, after this adjustment of removing the flow from the this one and putting this rigid arc separately, you get a set of network N4, and R4 is the set of rigid arc. For each of these, you will have the rigid arc, we will have one node in our next problem. And for the network, the final, whatever, here of course X5, those nodes, whichever that is there with some positive flow, positive availability will be there. Then we are adding now from so we are in a position to go to the next stage. So we have the current network corresponding to n equal to 4. Is that clear? That we are in a right place to stop and think about it. You can see that we start with given n and an x belonging to PMI n, and we have k equal to 4, because that's where we are starting. And then we construct F4. That's what we talked about now, and solve that. If F4 is feasible, then only we proceed. If F4 is not feasible, we stop. We don't have to do anything. We can conclude X does not belong to convex Pn. If it is feasible, then we are constructing the network N4, R4, and the mu is the weights for the rigid pedigrees. That's what we call mu. And once that is constructed, if it is k is equal to 4, then we go to the next one, k plus 1, that is the, now k will be 5. And then if k is less than n, of course, we can stop, because k is less than n, we can go further, consider whether x belongs to the convex pk. And it continues like that. Otherwise, of course, if already we have reached the end, we can conclude whether x belongs to Pn or not from there. Because if this has been gone through, then we know it x belongs to convex Pn. So these are the steps involved in this one. But what we have not yet completed is the construction of the layered network for k bigger than 4. Okay? So up to, we know what to do for 4, and then get the network for further processing. As I said, we need an initial network, then add the next layer, then find the capacity for the different arcs, or whether the arc should be there, and then solve the F4 problem, again F5 problem. And F5 problem is infeasible, we don't have to do anything. If it is feasible, we have to do something more. Then we will come to that later. So how do we construct this? So we take the original network, whatever nodes are there we take, along with whatever rigid pedigree nodes are there. These are all our origin nodes. And then of course we have the nodes corresponding to the next layer, that means the edges from E, K, and with some positive edges, only those edges we need. So that is added as our set of nodes, new set of nodes. So actually together we have, these are all the sets of nodes, and our sync nodes, or the final nodes, will be the ones corresponding to the EK, nodes in EK. And see, it might be interesting first to discuss some example with the six-city and show this, then go for mathematical this one. So that's what I'll be doing next. So I'll take a six-city problem and an example, then work out how we are developing the network. Then the same idea, of course, you can see it in the formal definition. One, a simpler, easier to understand this one is, if I want to avoid non-pedigree paths, I need to omit those things which will produce that. That means if I go through that, I will get a non-pedigree, means that somewhere it doesn't satisfy being a pedigree. So if I can avoid that, that means I'm making sure that whatever flow will be there will be of a pedigree one. Okay? So the pedigree flow is what we are trying to ensure by defining what is called the restricted network corresponding to that. So the restricted network is defined for each link that is possible between the last layer of the existing network and the next layer. So if you take one node from here, another node from there, then you can have a link. Now we want to know whether this link can be an arc with some capacity or not. That's all we are going to do. So given a link, we define a restricted network. The link, given the link, we make sure there are no nodes through which if you go have a flow along that, you will get a non-pedigree path or non-pedigree flow, which we don't want to have that. And this way of defining this, we should also ensure that we are not losing some important thing. That means, supposing a pedigree is required for writing x given k with some positive weight, and that pedigree will not be appearing in this, then we will be in trouble. So we have to prove results that such a thing will not happen. Okay. And these are the things that we need to work out. So once this network is constructed, we have got now the first problem is the FK problem. From early F4 to F5 we will do. And then if F5 is feasible, then only we go for doing a multi-commodity flow in the new network. So we say how to construct the new network. And that means we are adding this last layer and of course adjusting the capacities and other things according to the whatever rigid flow will be there, etc. So that is the next step where how we modify this network. So I will go through these things in detail in the subsequent section. Thank you.